All right, so we're going to talk a little bit about current in a circuit. And really, we're going to start with talking about um, what's happening on the atomic level in a wire. And so, what we've got are charges moving in the wire, and these charges are actually free electrons, and they're the ones that are far enough away from the nucleus so that the attraction is lower and they can move from atom to atom. And they don't go very far, but they do carry the energy, and the electric field accelerates those electrons along. And as they move, depending on the material, they collide and can lead to heat as well as carrying that electric energy. And so when we're talking about charges that are moving, we have to talk a little bit about the drift velocity, which is a quantity that characterizes how fast those charges are moving. And so it's basically 1 over the free charge density, which is how many charges you have in a certain area, times the charge times the area. And this leads us to current. Really, when we talk about electricity flowing, we're really not talking about drift velocity so much as we talk about current, which is the amount of charge that flows by a certain spot in a certain amount of time. So it's charge per unit time. And so we've already talked a little bit about it goes from positive to negative terminal of a battery. So it's the direction that a positive charge would flow. Even though we spend a whole lot of time talking about electrons, the conventional current is from positive to negative. And it can be either type charge that's moving, but we usually say it's electrons, and actually we run it in the backwards direction. Um, but bottom line is that the electric field causes the current to flow, and it's going to flow. So just keep that in mind. On circuit diagrams, it's going to go from plus to minus. And when we start working with circuits, you're going to need to know what direction it's flowing. And so, like I said before, it's the amount of charge that flows past a specific spot in an amount of time. And it is going to depend on the material that it's going through and the voltage that's driving it, because it is driven by the voltage or the electric field. And it's measured in amperes, which is that capital letter A. You can see the equations here. And if you want to do an instantaneous current, you just do the dq dt on a curve. And so it's just the change in charge over change in time. And we've talked a little bit about different kinds of densities. We have charge density, and now we have current density. And so it's a way to take the current and create a vector situation out of it. And it takes into account magnitude and direction of that small area of charge. And so it is the current divided by area. Just like any of the other densities have been, it's some quantity per unit area. And if you want to find the total current, which would be I, you would do the integral over the area of the dot product of the current density and the teeny tiny areas. So you're just adding up all those little areas in current products. Okay, I've got an example problem that works with current densities and charges. And we're going to start off with an accelerator that produces a half keV electron beam with a current of 0.8 of an amp. And we want to know what is the speed of the electrons in that beam. And if you remember, the electron volt is a measure of energy. So we have the electron volt is equal to the kinetic energy of those electrons, which makes it nice and straightforward to solve. So we end up with V squared is 2eV over the mass of the electrons. So we have 2 times 1.6 times 10 to the minus 19 coulombs. And then we have the 0.5 times 10 to the third volts. That's how we get that keV into volts, is multiply it by the charge on the electron. And then this is the mass of an electron. in kilograms. And so after you take the square root of everything, 1.3 times 10 to the 7 meters per second. So those things are moving pretty quickly, almost relativistically. So this may not be a very realistic problem. But if we just keep moving on and consider it cartoon physics if we need to, we want to know how many electrons are produced each second. And so we want to know what charge is moved, current times the time. So we take that 0.8 amps, and it's each second, so it's times 1 second. So every second, 1 coulomb goes by a certain spot that we're measuring. And if we want to know the number of electrons, it's going to be that charge divided by the charge on an electron. And so we get a whole lot of electrons cruising by every second. And so now we're going to talk about some current density. And so this is just current per unit area. And so we've got that 0.8 amps. And then we're going to consider the beam to be a cylinder. So it is going to be pi r squared. So it's pi times 1 millimeter squared. And we have to change those millimeters. And so we get 2.5 times 10 to the 5th amps per meter squared. So that is the current density of our electron beam. So here are some of the equations that we'll be using with current. All right, so these equations are pretty straightforward. You have the average electric current, which is the change in charge over time. An amp is a coulomb per second. Electric current, when we're talking about on the tiny level, is dq dt, and then you would integrate the current density dot product with the area vector, and then we're back up to the drift velocity, which is the charge times the charge density times the area.